So welcome up, Marcel, and looking forward to your talk.
Thank you very much, Thomas, for the introduction. Yeah, so my name is Marcel Markgraf. I'm from the company Base Labs, and today I will talk about next-generation sensor fusion for next-generation sensors and driving functions. And for those of you who know Base Labs, that probably know that we are focused very much on sensor fusion. So we dig very deep, as Thomas introduced, into the core functional and algorithmic development. In my talk, I will basically have two key takeaways. The first is that current sensor fusion approaches that we see in ADAS have inherent limitations that also limit their applicability for next-generation sensors and next-generation driving functions. And we at Base Labs believe there exist integrated sensor fusion approaches today that can help to overcome those limitations. But what are next-generation driving functions in my talk? Well, I'm thinking of automated emergency braking, automated emergency steering, and also adaptive cruise control, but actually and really working inside of cities, taking us closer to automated driving, or even automated parking, like valet parking or train parking. Those kind of functions that we see emerging where a lot of parts in the industry are working on bringing them on the road right now. But also traffic jam pilots, highway pilots. This is what we see the next generation of ADAS functions bringing us closer to automated driving. Well, what are the requirements for those kind of functions? We see an example here. And we have an urban environment with all kinds of static objects. And as we have seen or heard in the talk before, we need to identify all of those objects. And it's not always clear if the system has seen them again, or if the lighting is weird, or if something is odd about the situation. For a higher level of automation, for more trust of the public into those systems, we need to identify all kinds of static objects. There's another example. We have many vulnerable traffic participants, like those children. And here we have an AEB that actually works properly. And I would assume that AEBs today make good work and they prevent many harmful accidents. But I believe we can also do better. And for autonomous driving, we need to do better. We need to protect basically everyone that we can. So from our perspective, the requirements for next-generation driving functions are the following. We have many different static and stationary objects, many different kinds, shapes, and forms that we might have not seen before. We have many different traffic participants, like here in this example, pedestrians, bicyclists, bike riders, cars, trucks, all kinds of stuff, and stuff that we can't even imagine. And we have a very high number of complex scenarios. As we have heard before, we need to shrink them down to the ODD. We need to reduce complexity, but the closer we move into urban environments, the higher the complexity will be anyhow. And we want to increase the level of automation. Ideally, in the future, we want to drive autonomously. And this brings in more challenges. So what are the challenges from our perspective for a sensor fusion company? Well, we need to think about how an ideal environmental model that basically is the output of the sensor fusion after combining different inputs from different sensors looks like. Well, ideally, we have information about all the dynamic objects, but not only where they are, but also what their extensions are, what their velocity is, what their heading is. And we also need to understand all kinds of static objects, regardless of what shape or form or visual appearance they have. And, well, combining static and dynamic objects, what is the rest? That's free space. And that's a critical information for doing maneuvering decisions and for actually steering, throttling, and braking accordingly. And the next factor that actually enables next generation ADAS and also automated driving is high-resolution sensors. You see those examples down here, if it works. Those are radars. So we see emerging radars now with a very high resolution that bring in a lot of information. We see cameras like semantic segmentation cameras, where you have a very high-definition information about the environment. You see depth images, cameras that provide those, or LiDAR sensors could potentially be used in the future, bringing a very high-resolution point cloud with a lot of information about the environment. And what we are concerned with and focus on as a company, as I said before, is the sensor fusion. And the question is, how do you fuse that information together without missing any information, without missing the pole that we have seen before, and with identifying all of the traffic participants? Well, current systems, and I'm not able to judge all current systems, but what we see often in the industry nowadays and in the systems that we have seen is a combination of dynamic object fusion and static grid fusion. So there are two basically separate algorithms. The dynamic object fusion outputs the dynamic objects and processes all the measurements for the dynamic objects. And the static grid fusion runs in parallel and provides the static environment and the free space. Well, this approach is very well suited for larger distances of objects. And it's also very well suited for a highly structured environment where everything is more or less structured in a good manner for the function to work properly. And one key benefit of this approach is it's highly modular. So you can develop both aspects, both algorithm parts individually. You can even ship them individually for different driving functions, or you can combine them together, which is a benefit for the cost of the development and also the cost of the distribution. And they support current generation, rather low resolution sensors. However, when you look at them closely and when you look at them thinking of next generation driving functions, next generation high resolution sensors, you see inherent limitations that they have. And let's talk about the limitations of the dynamic object fusion first. As I said before, for larger distances and rather small objects, this is where dynamic object fusion was built for. This is what the core algorithms are built for. It's probably a Kalman filter approach or something similar. And the closer the objects get, and the larger and the higher the extensions the objects are, and the more measurements we get from the extensions, the more limited the performance of these kinds of algorithms is. On top of that, dynamic object fusion often requires a priori knowledge about the objects. What kind of objects will we see? What is their motion patterns? How do they appear? And this introduces an inherent risk to miss previously unknown objects and to potentially have an accident caused by that. Additionally, if you have high-resolution sensors, like high-resolution radar, camera images, or a LiDAR point cloud, you cannot process them directly in an object fusion approach. You need to basically do an object extraction, a clustering, some form of combination into objects very early on. And, well, when this works ideally, as we see here, if the clustering, the object extraction works properly, then everything is fine. However, if this initial and very crucial step has errors, then those errors are introduced in the system early on, and you cannot do anything about them anymore because you already did the decision. You didn't use the measurements in the right way, and you didn't interpret the scene in the right way. So overall, this introduces a high risk in challenging scenarios. So let's look at the static grid fusion. And also the static grid fusion has quite some limitations. A static grid, the output might look something like this in a schematic way. So you have free space in green, and you have occupied space in red. Everything is in a grid, so there's an algorithm calculating the the probability of a grid cell being occupied or being free space. However, an occupancy grid, a typical occupancy grid, is a static occupancy grid, and it assumes the environment to also be static. But we have seen before, we want to take into account a lot of traffic participants of different shapes and forms. And what happens if you use sensors and if you put them into a static grid algorithm and you look at the output, then you see those tails behind the objects. So that's outdated free space. They have been seen there before, so even if they move, there's a high probability, or the algorithm cannot say whether this is now free space again and they moved, or whether there has not just been a confirmation by a different sensor. So basically, the free space shrinks down, you have those object trails, and you limit your ability to maneuver. There's a workaround. And we believe this is typically being done. You can take the dynamic objects from the dynamic object fusion and basically stamp those measurements out. And you basically disregard all the measurements originating from dynamic objects, and then you just process all the measurements that you believe originate from the static environment. And if the dynamic object fusion and the object extraction work in a proper way and work as expected, this approach is fine. However, if, as we have seen before, the object extraction or the dynamic object fusion is erroneous, then you propagate those errors from the dynamic object fusion into the static grid fusion, and this again introduces a high risk to fail in challenging scenarios. So, concluding, we believe that in order to cope with those limitations, you need a truly integrated approach for sensor fusion. You need an output where you truly have dynamic objects, static objects, and free space. And this is known as grid fusion or dynamic grid fusion. And this is what I want to highlight today. And this is basically the second takeaway. We believe that such integrated sensor fusion approaches can limit the restrictions and limitations of today's systems. So how does a dynamic grid fusion look like, or how does the output look like? We see the example here, or one example here in the middle. Again, free space is indicated in green, so you have like what you see here is an image with many small grid cells. Free space is green, statically occupied space is red, and dynamically occupied space is blue. When we start moving, we see how the ego vehicle is turning on a parking lot, and we see how the free space is accurately being identified in front of the vehicle. When we go onto the road, we encounter a bicyclist. And this bicyclist is marked by blue cells, so it's identified, and we also see there's not many tails after the objects. And we also see that here with the roundabout and the crossing van that we have a quite reliable velocity and heading measurement also, or identification also. Here we have a stopped vehicle next to us and one moving car approaching from behind that now turns into a stopped car because it's stopped. When we start moving again, the car behind us also starts moving again and turns into a dynamic object again. Moving fast forward, we encounter a construction site with quite similar poles that we have seen earlier. And those very small poles that are lined up here are also identified and marked as static object. And we have heard at this conference before that identifying static objects and static cars and differentiating them from moving cars is a challenging task. This integrated approach, and here we see a very complex scenario at a roundabout, allows us to do all of that in an integrated manner, not missing out information early on, and not judging the situation early on, but allowing us to take the judgment much, much later in the processing step. And last but not least, we see a truly extended object here, which is a rather large bus, which is also identified in its extensions, but also as a moving object with velocity and heading. And we believe this allows the following driving functions to make very good predictions onto the future occupancy, free space, the motion of dynamic objects. And this introduces the ability to make safe driving decisions. So how does it work? Well, the dynamic grid has one parent, inherits from the static occupancy grid. So as you've seen before, the static occupancy grid indicates free space, non-occupied space, and occupied space. What the dynamic grid also introduces is particles. So all of those grid cells are populated by particles, and those particles contain the dynamic motion hypotheses. So when there's many particles moving into the same direction with the same velocity, then the probability is high that the object that this grid cell belongs to is also moving into that direction with that heading. So all of those particles are independent, all of the cells are independent. And that way, we can determine the motion of arbitrary objects with arbitrary shapes, arbitrary sizes, without any prior information about them. And one side effect of this approach is that we can tune the number of particles in the grid according to the level of occupancy. So when there's free space, we don't need many particles. If there is static objects for a while, then we can reduce the number of particles. And when there's dynamic objects, we can introduce more particles in order to more accurately determine the dynamic motion. And this allows us to tune this algorithm to performance and allows us to bring those kind of algorithms onto today's automotive CPUs. So we don't need a GPU or a fancy, very powerful computation device. And you see some examples here. So in gray, you see an example with a 4 HD radar system, so radars surrounding the ego vehicle, or in green, a system with 4 HD radars and 4 semantic segmentation cameras. So it's quite a computational load that's on the system. It's quite a lot of measurements that need to be processed. And depending on the grid cells, and we put on typical grid sizes like 300 by 300 or up to 500 by 500, we can achieve refresh rates from 100 hertz to 40 hertz. And we're still working on computational performance. But we believe this allows us to put this kind of algorithms on today's and next generation hardware with next generation sensors. And on top of that, we can not only have the occupancy as one channel. If there is sensors like a semantic segmentation camera or even LiDAR process data where you have information about what it is that you perceive, you can also introduce them into the dynamic grid, and you can have a second channel indicating not only the occupancy, but also what it is that you see in front of you. So here in this example, we could, if this information would be available from a sensor, denote that there's a person, that there are two-wheelers, that there are cars, trucks, poles. So we can distinguish different objects and obstacles. We can also distinguish different areas of free space, like a sidewalk, a road, lane markings, parking areas, or whatever the camera or other sensors can identify. All of that can be introduced in the algorithm as well. Or often or sometimes, there's something, but don't know what it is, and this could obviously be denoted as well. So what are the key benefits of this approach? Well, the first main benefit is a very high detection rate. And this is basically done by low-level sensor fusion without early-on object extraction. The main goal is to not disregard any of the measurements and to take them all into account and to have a very complete picture of the environment. The second benefit is a low false alarm rate, because it's not only that you have to be conservative, you also need to avoid braking or doing maneuvers that are actually not required. And this is being done by an integrated estimation of dynamic and static objects, by doing everything simultaneously. And the third benefit is that the algorithmic approach allows us to bring this onto automotive-grade CPUs by optimizing and minimizing the particle load in certain areas of the dynamic grid. So, coming back to the key takeaways, so we believe current sensor fusion systems have inherent limitations, but those limitations can be overcome with currently available integrated sensor fusion approaches like the dynamic grid. We at Baselabs, we call it Baselabs Dynamic Grid. It is an integrated sensor fusion technology, as I've shown. It's automotive-grade, CPU-ready, it's white box, and we believe it can be get to production right now. So I hope this was worthwhile for you, and I thank you very much for your attention.
So great, thank you for the presentation.
Thank you.
And of course, I'm wondering, is there questions out there? There you go.
Andreas Löffler from Conti.
Hi.
Yeah, hi. Thanks for the presentation. Just wondering, is there in your grid already an idea on how to bring in the elevation? So I mean the height information, so when I got per range cell, if I look at from top several, let's say several targets.
Yeah, we're currently working on this. So there's different ways how you could do it. Well, you could have a 3D grid, but then you would have a very high computational load again. What we currently are following is that you basically don't know the full resolution into the vertical dimension. What you need is, can I pass it over and can I pass it under? And this is basically two kinds of information. So we are currently following a strategy where we will have basically a second channel. Is it possible to pass under, and is it possible to pass over? And that would then be that information also.
I think that's a good approach. I think for the lower cost sensors. But what about the 4D sensors when you really have that elevation information? So when you really got that measurement, let's
well, then it's going to be a trade-off again. Will you disregard information again for computational reasons, or will you take it into account? So it would be possible to take it into account, but then you need to optimize that.
So it's just memory and then computational power, which will go up in the third dimension, I guess.
For the current generation, yes.
Okay, thanks.
All right, great. Any other questions? In that case, I'll ask a question. So when talking about perception systems, I think even our last speaker mentioned a lot about reaching the necessary performance often requires machine learning. And seeing here, I didn't see too much of it. So how does this work in relation to kind of that needed precision?
To machine learning?
Yeah.
Well, for a long time, I perceived the community as it's either classical sensor fusion or AI. And I come to believe that it's classical sensor fusion and AI. And there's two steps where I believe machine learning comes in. First, we have seen the semantic segmentation information that was provided by a camera. So I believe there's probably machine learning being involved there. So the sensors may have internal or already do pre-processing with machine learning. And then as a second step, we strongly believe that the dynamic grid is an ideal input for machine learning decision making and basically prediction of the future. So we believe that in order to predict free space and the motion of objects, in the future, like 2, 3, 4, 5 seconds, depending on the driving function, that this would be done by a machine learning approach. At least this is an architecture that we believe makes a lot of sense. And this machine learning approach then takes the dynamic grid as an image input and then process it to make decisions, predict future events. But we believe the dynamic grid is an ideal way to bring all of the information together and to allow for the algorithm to make these predictions without lacking information that we have disregarded beforehand.
Cool. All right. If no further questions, then thanks for this. Great talk.
Thank you very much.
And big applause.